everyone to get the fastest answer. So a lot of the session will take engagement from you as well. I won't just be talking at you. I'll be waiting for you to answer my questions, and I'll be answering questions that you give me at various points. We'll have 3 times when I'm answering your questions live on the camera. So that's today. I'm not going to reveal the Slido code until we say, so please stop asking. So here's our topics for today. We are going to talk about fractional distillation. Now, if you do know about fractional distillation, then that's great. If you don't worry, because we're going to be going through it completely. We're going to be talking about alkanes and hydrocarbons. We're going to be talking about alkenes and combustion. We're going to be talking about cracking. And I'm going to add a little bit extra in today to talk about carbon chemistry, because this ties in everything we need to know about the subject. But we are going to have to look at what we've previously done to make sure it's cemented. So if you think about knowledge, it's like building a house. You've got to have a nice flat ground before you can build on top of it. So that's what we're hoping to do today. So I'm not going to jump in and start talking about hard concepts until we are all at the same level as talking about those other fundamental concepts that feed into it. So learning objectives today are: explain how carbon bonds. So how does carbon as an element bond to other elements? And it's not as simple as it always would seem. But we're going to talk about fractional distillation, so that term again that we've just talked about. We're going to talk about components in crude oil. So we know oil basically is very important. You might have heard about it on the news recently as being something that's kind of less available to us. And it goes through waves of sometimes it's really available, sometimes it's not. And it basically controls a lot of how society works. So we're going to learn about why. We're also going to talk about alkanes. So if you've heard about alkanes, then cool. If you haven't, then don't worry, because we're going to talk about that in lots of detail. We are also going to talk about the structure of those alkanes. We're going to talk about formulas of those alkanes, so practicing chemical formulas if you want some more practice on that. We're going to talk about balancing equations just in the concept of combustion. We're also going to talk about hydrocarbons, boiling points, this word viscosity, what that means. We've got to do loads. Catalytic cracking, steam cracking. You can read the slides yourself to find out exactly what we're doing, but you can see there's going to be a lot of stuff today. But the fun news is it's all very relatable to the real world. So hopefully it will give you an understanding of how the energy industry works, how cars are based on oil, how do we get oil, why we need oil, why there's a lot of money in oil, how oil influences the economy. So basically you'll be able to understand the news better, which is important. So atoms. Let's talk about atoms. We can't talk about chemistry without talking about atoms. Now, we've already seen this slide before, if you've been with us before, because this is an old slide, which is why I had that previous presentation. So I'm not expecting this to be new to you. If it is, then okay. But if it isn't, then that's pretty much where I assume we are. So everything we know in the world is made out of atoms. So if you think about it, we could break lots of things up into tiny balls. And once we get past these tiny balls, we can't actually separate them any further than that. So if I have what do I have around me? A ruler made of wood. I could technically, if I had all the instruments I need, take a wood chunk, keep dividing it and dividing it and dividing it until I get something as small as possible. And that small as possible thing would be an atom. So that I could say, if that's the smallest thing I could get from my ruler, then I guess my ruler is made up of billions of those tiny things, and they are atoms. So I've got a ton of atoms in my ruler, I've got a ton of atoms in my AirPods, I've got a ton of atoms in my speaker. I'm made of atoms pretty well. There is nothing around you that isn't made of atoms. The only place where we would find an absence of atoms is in space, and that's why space is referred to as a vacuum. So atoms are tiny things that make up everything else. Now, atoms are named depending on what is inside the atoms. So I'm not going to talk about this in too much detail, but atoms are different because inside each atom can be a different combination of protons, neutrons, and electrons. So depending on what these counts of protons, counts of neutrons, and counts of electrons are, depends on what the atom is. So we talk about different, if you take a deck of cards and you look in the deck of cards, you will see that there might be queen cards, king cards, jack cards. They are all the instances of cards. We have different types of cards. So you could say we have 4 suits of cards. Cards can be any of those 4 suits, or an ace or a joker. so a bit more. Now, atoms, instead of having 4 types, we have 118 different types. And all of these different types are referred to as elements. So that's where we go from atoms, meaning one, to elements, meaning different types of atoms. And every element is different because element number 1 has 1 proton. Element number 2 has 2 protons. Element number 3 has 3 protons. Now, these two vary a bit more, but proton number defines the atom. So just like you are defined by your name and maybe your age and maybe what you like to do and your personality, atoms are defined by their proton number. So I can distinguish 2 different things, not by just their name, but their proton number. So I can point at an atom of gold and say that's different to an atom of carbon because the proton number is different. So that's very helpful. So you are not seeing these slides, by the way. I just saw someone's question. These slides are taken from an old presentation. I thought these would be supplementary to our presentation. So you won't be seeing these slides in your own pack today, but I'm talking about them because they relate to today. So we are made of atoms, and everything, solids, liquids, gases, is made of atoms. And we know that different types of atoms are called elements. So elements can be things like gold, can be things like silver. They're not things like water, but water is made of elements because water is made of hydrogen and oxygen. So they are different. So water is made of 2 elements. Carbon is an element, so it's just made of carbon. Oxygen is made of oxygen, so that's an element. Whereas sodium is made of sodium, so that's an element. So all our different elements are the different types of atoms that we see. So compounds now are when we mix different elements together and we bond those atoms. So a compound that we've seen before is water. Water is a compound because H2O contains the atom hydrogen taken from one element and the atom oxygen taken from another element. So I have 2 elements here coming together to form a group. That is a compound. If the elements are not different, we can't call it compound. But in our water, we have 2 different elements, so it's a compound. So now that we have established what compounds are, we've established what our elements are, we've established what atoms are, let's now talk about the difference between a compound and a molecule. So compounds, we have to have different types of elements. This is hydrogen, and this is oxygen. So water is a compound. Water is your go-to example when you're thinking about compounds. Now, what's not a compound is something like H2. I've got 2 hydrogens joined together. There's 2 of them, so it's not just one element. Well, it is an element, but it's 2 atoms. So it's not just one atom, it's 2 atoms. But 2 of the same atoms bonded together, which means chemically joined together, is what we call a molecule. So it's a bit confusing. We would say all compounds are molecules because we have 2 or more atoms joined together, 1 and 2, but not all compounds are molecules. Sorry, not all molecules are compounds because our molecules are when the elements can be the same or could be different. So I'm going to draw to you a molecule. Here's a molecule. Here is another molecule. Here is another molecule. This is a molecule. But did you see how I draw H and H? Even though they're the same element, it's still a molecule. But I can't call that a compound. So it's a molecule, but it's not a compound because they are not different. Okay, so now we know what compounds are. We know what elements are. I think we're doing great. So a molecule is simply 2 or more atoms joined together by a chemical bond. And we like to draw that chemical bond often when we're representing what the element is by drawing little sticks. So if I'm drawing water, I draw H, stick, O, stick, H, because the hydrogen is connected to the oxygen is connected to the hydrogen. So what I have here is water, H2O. So we have 2 ways of displaying it. I can display it like this, which is its molecular formula, and I can display it like this, which is its displayed formula. So I'm displaying the bonds. Now we've seen here that I have a 1 stick. What can actually happen between 2 atoms is I can have 2 sticks. So I could have a carbon atom stuck not once to a hydrogen. Well, it could be stuck once to a hydrogen. I could have a carbon then stuck to another carbon atom here, because carbon is an element, and these 2 are atoms of those elements. But I could have a double bond. So it's not just 1 connection, it's 2 connections. So now these atoms are very strongly held together. It's like applying 2 coats of glue to something. It's going to stick better. If something slides off because it's really heavy and you think, oh, it won't stick very well, you'll add more glue and it will stick. And that's what we're doing here. We're gluing these atoms together with a bit more power. So I'm adding not 1 bond, but 2. So molecules are just a combination of atoms in a group with chemical bonds. So again, this is a molecule. This is a molecule. This is a molecule. This, now look at this. This is an N. Sorry, that doesn't look like an N. It looks like a W. Let me try again. This is a molecule. Now we have 1 connection, 2 connections, 3 connections. This is the molecule N2, nitrogen. And this is what makes up most of the air that we are breathing. Nitrogen is N, nitrogen, bonded to N with a triple connection. So there's a triple connection between 2 atoms here. And that means it's very strong. There's no way I can pull these atoms apart. And that's why it's found in air. It's so stable, it's not going to go anywhere. So most of the air we breathe is actually nitrogen, but we want the oxygen. So we just care about oxygen. Anyway, molecules, 2 or more atoms joined together by chemical bonds. So now we have established these things. And we know what molecules are. There's some more examples of molecules that I have here. So I have O2. Again, there would be a connection between these 2 atoms. There would actually be 2 bonds. So we call this a double bond. That kind of makes sense, doesn't it? Because 2 means double. Hydrogen, when it's connected to a hydrogen, is just a single bond. I'm not expecting you to know this or learn this. This is just fun facts for you. That's a single bond. It's a single connection. Now, this is phosphorus. The element P stands for phosphorus. And we can have 1, 2, 3, 4 bonds, but between 4 atoms. So here it's all single bonds because it's not like it's 2 connections per pair. It's just 1 connection per pair. 1, 2, 3, and 4. But it's all single bonded. So this is a molecule, but is it a compound? No, because they're not different elements. This is a molecule. Is it a compound? Nope, because they're not different elements. This is a molecule. Is it a compound? No, because it's not different elements. So you should be really checking to see if it's a compound by seeing if the elements are different. Okay, so I think we are kind of nearly there in my summary of what I want to say about things we know around us. So molecules are when we have any 2 atoms joined together. We can only call them a compound if they are different from one another. But all the time, it's about joining of things. So what can happen in the world, in the universe, is it's not just I'm joining 1 atom to another atom to make CH. Quite often what's actually happening is I'm joining molecules together. So I'm joining an O2 and maybe some carbon with some hydrogen, with 4 hydrogens. So I'm joining this molecule with this molecule, C, with 4 hydrogens connected to it. And I am making a new substance. Now, that new substance I'm making isn't just simply me adding together things. A lot of the times, our chemical reactions involve us rearranging things. So what's going to happen here is my carbon sees 2 oxygens and says, oh, carbon dioxide. I love it. It's my favorite food. And it starts to make carbon dioxide. Now, if we look behind, we've got lots of hydrogens here. So it steals some oxygen from somewhere else. The hydrogen steals some oxygen, and they love to make water, so it makes water. So this hydrogen and this hydrogen might buddy up and steal an oxygen and make water, and this carbon has obviously stolen those oxygens to make carbon dioxide. So molecules are often combined in our chemical reactions. When we think about chemical reactions, adding 1 substance to another, it's actually often the combination of molecules, not just adding 1 atom to another atom. That's too unlikely. In the universe, everything already tends to exist as a molecule, and often we actually have to break things out of their molecule and put them in new molecules. So that's what we mean. Now, when I talk about the air, I've already mentioned this. The air that we are breathing in, you might think is predominantly oxygen. It is not. Even though we need the oxygen for respiration, which you will learn about in biology, the air that we are breathing in is 78% nitrogen. Now, this nitrogen, I will show you, is not single N atoms floating around. It's not this. When we take a big gasp of air, we are not breathing this kind of system in. What we are actually breathing in, let's see if I can get this right. I always get the rubber one. Okay. What we are actually breathing in is groups of nitrogen expressed as a molecule. So we're breathing in N triple bonded to N, N triple bonded to N, N triple bonded to N. Now, we don't really do much with this other than spit it back out again. We might even be able to filter this out the air. I'm not really sure. But this is mostly what's in the air. So if we look at about the universe, well, I keep saying the universe, Earth's atmosphere is 78% nitrogen gas. So we are actually there for the 21%. You know, we're there for the minority. We want the oxygen. But the nitrogen doesn't harm us because, like I said, that triple bond is so strong between those N atoms, they're not going to go away and react. They're not going to form anything new. It's not going to harm us. So we're fine. So what we want is this molecule O2. So in hospitals, you might see that doctors administer this to patients if they don't think they're getting enough oxygen themselves from breathing in. Maybe they've got a problem with their airways. They might give them oxygen. Oxygen is just O2. So oxygen is represented by 2 oxygen atoms with a double bond between them, O2. So I'm paying a lot of attention here to talking about bonds today. Bonds are actually very important into chemistry. Bonds make up most of how chemicals work. It's all about their bonding. Things can be very different based on the way that they're bonded. So if I'm looking at a substance like this, P, 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 it's very different to a single P atom. Just like how Cl to Cl is very different to Cl on its own. So the way that things bond basically changes how they are. And a way you can think about that is think about you on a day when maybe you've not had breakfast. You might not say things that are very nice to other people. You might be a bit more hungry and angry, angry and angry, hungry. And that doesn't mean that you're always angry. It just means in that particular moment you are angry. And that's because your day has been set up not very well. You didn't have breakfast. You're probably a bit hungry. And maybe a bit agitated. So you kind of go ahead and maybe you yell at someone, or maybe you just forget something because you're a bit more kind of lethargic. So that idea of you being different in that behavior is because something was different about you. And that's like our chemicals. So how our chemicals respond, and when I mean chemicals, I really mean any atom in the periodic table. How atoms respond is really about how they are with other atoms and how they're connected to maybe themselves and other atoms. So oxygen is a molecule and oxygen is an atom. It's weird. It's weird that it's both, but it is. I wish they'd call it something else. Technically, you could call this dioxygen, but no one in the chemistry world would ever actually call it that. So that's a fake name. But if it makes you feel any better, you could try and do that. But if we're referring to oxygen that we're breathing in, we're actually breathing O2. Again, it's never a scenario when we're breathing in separate oxygen atoms. So most of the things we're breathing in are molecules, and our body is rearranging these things into other molecules. Now, there's another part of the air which is changing, and that is carbon dioxide. Now, obviously, we're breathing out carbon dioxide, but we're also producing it in large amounts from burning substances. And photosynthesis, when it stops, limits itself at night, and plants respire more, they're also producing this. So burning is producing this. Respiration of animals is producing this. It's already kind of kicking around in the atmosphere, and it's cycling through the oceans as well. But what's happening now is that we have gone crazy with this. We have not monitored our use of carbon dioxide. Well, I say we, I'm not really me. It's the current state of affairs. So the fact that our cars are burning this, making this, our factories are making this, our airplanes are making this, most of the things that power stations are making this. So this substance CO2 we've heard about before, maybe in the news, as being something that we have to be careful about, because what this can do is cause a absorbance of heat around the Earth, and it can absorb more heat than we want it to. So if we have more of this, it can absorb more heat, and what that does is it raises the core temperature of the Earth, so that our weather systems become really, really kind of disgruntled at the fact that England is not feeling as cold as it used to, or maybe Australia is feeling colder. So those differences are changing our weather systems, our ecosystems, our habitats of animals, our populations of animals, our populations of plants. So that's going to be very destructive to the planet. So CO2 is something that's produced normally in the air, but now I would say CO2 is probably going above this kind of 2%. And that's changing the environment that we are in. That's why you obviously see a lot of people talking about limiting carbon emissions. We're talking about this molecule here. We obviously breathe this out, so it's not terrible. It's not toxic, really, unless you can't have any oxygen. Anything's toxic if you don't get oxygen. But what this is doing is it's absorbing heat very well, and we don't want that. So those are some molecules we've come across all the time. Again, we're not breathing in a lot of single atoms. We're not dealing with single atoms. When you take a drink, you're dealing with a molecule. When you do maybe have some food, you're dealing with this molecule here, which is glucose. So when you're having food and you're getting nutrients from food and you're feeling more energized, it's often because of this molecule. But this time it's a much bigger molecule because it's got 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So it's quite big. So molecules don't have to be just 3 atoms big. They can be 100 atoms big. They can be 1,000 atoms big. They are everywhere. Now, chemical formulas of molecules obviously tell us what is in it. So here in water, we have H2O as our chemical formula. We probably know this pretty much it's given everywhere. If you look on the back of a water bottle, it's probably on there. It's on a lot of adverts, and people say H2O because it's just what's in water. So our chemical formulas reveal what atoms of what elements are in our water. So it's almost like what's in my bag. It's saying, what have I got here? Inside this molecule, inside this package, what is in there? So, it's kind of like a little clothing haul, if you will, of everything that's in there. So for salt, a molecule we've all come across, salt is made up of the atoms sodium, given by the symbol Na, and chloride, given by the symbol Cl. So that's our salt, 1 sodium, 1 chlorine. Now, you're not expected to be able to remember all of these symbols, but you have this amazing kind of dictionary to tell you what you need to know, and it will never be hidden away from you. So you never really need to learn this or memorize this in the periodic table. If you don't know what any of these symbols are, you've seen Na and you don't know what that means, you go and look for Na in your periodic table, and you will find it right here. So Na is found over here in your periodic table. So if you don't know what the symbol K means, you look at that in the periodic table and it tells you. If you don't know what the symbol Fe means, you don't go ahead and learn all of these things because that's a waste of energy and you've got other things to waste your energy on. But you do go look at the periodic table. So from my periodic table, I look at C, I find it's carbon. I look at H, I find it's hydrogen. And I look at O and I find it's oxygen. I then go and look at the next one, and I've got acetic acid, which is basically the chemical name for vinegar. So acetic acid is made of 2 carbons, 3 hydrogens, and 2 oxygens. That tells me I need this many atoms. So you can think of these as adding together to give us a total number, okay? Because they're all atoms at the end of the day. So the total number of atoms in this is 2. The total number of atoms in this is 12. Add 11, which is 23, add 22, which is 45. Then 2 is 7, and then sodium bicarbonate, which we've all come across in food as well. Na, we've got Na again, we love sodium today, which is 1 sodium, shown by no number next to it, 1 hydrogen, 1 carbon, and 3 oxygens. So I'm not saying anything new here, I don't think, unless you've not been with us for the previous sessions. But one thing I want to point out is that we don't give little ones. So when we only have 1 of these atoms in the molecule, I'm not writing Na1. We do not do that. That would be wrong. And if you did that in an exam, you might not get it right. So make sure that when we're writing sodium, you're writing a little absence of a 1. You're just writing this. If there's 1 atom, you're writing this. If there's 2, you're writing your 2. So I'm going to now switch to our Slido part of the day where I ask a little question. So my question for you, for y'all, is what is the chemical symbol for carbon monoxide? Now, I'm just writing this as I speak because I feel like this is a good question. So I am going to project this onto the screen in a few minutes, maybe a few seconds. And I want you to pay close attention to the way I'm capitalizing my answers that you can pick from, the way I'm providing numbers. All of these things are very important. Okay. Let's do this one. Boom. So now we're in the Slido part of the day, everyone's favorite day. So what's going to happen here is you can take your code, QR code, and you can scan it, or you with a camera, iPhone, whatever. Then alternatively, you can go on to slido.com and enter the code that we're all asking for, 295398. 295398. So I don't want to see your answers in the chat. I will not want to do many of these if you put your answers in the chat, but I do want to see your answers being given on your personal device or on your own computer right now, so I can see your answers on here. When I can see your answers on here, I know that we have maybe 80 people in the call today. So when we get towards 70 or 80 people, I'm going to move on and talk about our answers. So if you didn't get the chance to answer, everyone else might have jumped in before you, and I can't wait for every single person. I don't know if you're in the back room or not. So I will kind of move on when we get to about 70 people. So I want you to tell me the chemical symbol for carbon monoxide. Now, I haven't gone through this word at all. This isn't something that's like a memory test. I've used a new chemical molecule and I'm asking you about it. So I want to know, you know, the chemical symbol for carbon monoxide. If you don't know what the word monoxide means, that's my next point, so don't worry. If you do know, then great. Either way, we're going to get to talking about it, so alas, do not fear. Okay, I'll wait for 5 more people to answer. So if you're one of the last, I don't know, 20 people to not answer, try and answer, just so I have a good marker to know when to stop. It looks like a lot of people are going for CO. So we've got a capital C and a capital O. So to talk about this answer, you would be correct if you put CO. The reason why you're correct is because carbon is given in a C symbol, and we only need one of them, so we don't write a number next to it. The next one is O, and monoxide refers to having one of the atoms in the molecule. So nitrogen monoxide is NO, carbon monoxide is CO. Now, the reason why it's a big O and not a little o is if we have C and a little o, we are talking about a brand new element. Anytime you see a lowercase letter, it's connected to the left uppercase letter. So, for example, the atom iron, or the element iron, has the symbol capital F, lowercase e. Now, that lowercase e denotes that the whole thing is to be read as 2 letters at once, Fe. Some symbols in the periodic table are just F. Some symbols are Fe. Now, the reason why is because iron, I think the Latin name for iron is like ferrous or something like that. They've used up some symbols, so they have to give symbols to other atoms, and then they get confusing names. So some symbols in the periodic table have 2 letters to themselves, some have 1. Carbon is just C, oxygen is just O. We only have 1 C and 1 O. Now, if you put CO2, that definitely is talked about a lot, but that's carbon dioxide. So we're using that kind of word di, which you might have heard of in other respects. I'm trying to think of other things that have the word di in them. Di, I think it's Latin or Greek, or some sort of root word for 2. Same as bicycle, meaning 2 wheels ridden at once. Bi. Di and bi often refer to as 2. Mono often refers to as 1. So that's why the answer is CO. Now, the time is 10:35, so we're going to take our first break. So I'm going to stop that for now. Well done if you did your first Slido with me. Have fun. We're going to take a 5-minute break, and then we're going to move on to our continuing our slides. So I will see everyone back here at 10:40. Okay, I was on mute. Welcome back from our break. The time is now 10:40/10:41. So I'm going to welcome everyone back with a Slido question. So I'd like everyone to join and answer my question. Okay, you can see we have some votes already. Oh, that was the old one. Okay, sorry about that. Here we go. Here's our next question. So how many atoms are there in total in this molecule here? So I'm not going to tell you how to do it until a few people have answered. Lots of answers to pick from. You choose which one you think would make the most sense. Okay, we'll wait for a few more people to come back from their break and answer the question, and then we'll move on. I don't want to move too quickly on these ones because we need to give everyone a fair chance to answer, especially when we're coming off a break. So when you are back, please answer this as quick as you can so that we do not delay with everything else we want to do today. So how many atoms are there in total in the molecule C6H12O6? Okay, it looks like most of us are answering the question who want to answer it. So I'm going to talk about the response. So a lot of you said 24. You would be right. A few people said 23. I assume this was probably just a miscalculation because what we should be doing here is adding 6 to 12 to 6. Now 6 to 12 is 18, and another 6 is 24. So what I'm trying to get at in this question is the idea that a molecule is a bundle of atoms, and you could count each one individually and have a total number of atoms in a molecule. So you need to see molecules as groups of atoms, as you would see compounds as groups of atoms, except molecule, we're not telling everyone whether those atoms are different or not. So all molecules have groups of atoms in them, but compounds are when those atoms are of different elements. Now, if you said 12, which actually no one has, that would be not considering the fact that all of these atoms are grouped together to be considered a molecule. So that right there was glucose. If you've ever heard of glucose before, you'll know it's a super important molecule in our body. We can't really survive without it. It helps us do something called respiration, which basically converts to energy in our body and gives us the energy we need to move, breathe, see, think, beat our hearts, everything. So without this molecule, we wouldn't really have much life going on. So you will see this molecule again and again in biology, which is why I often talk about it in chemistry so you actually understand what the molecule is. So thanks for answering my quiz. Now let's talk about my next point, which is the periodic table. So we've talked about this as a kind of dictionary. And the reason why I think dictionary is if you think about a dictionary, no one expects you to learn an entire dictionary to say that you can speak a language. What you would say is that if you want to find out more about the words of the language, you look in the dictionary. So for the English language, if I want to know all of the words beginning with D, I'm going to look at D and look at all the words beginning with D. That doesn't mean I need to know every single word beginning with D. There's a lot of words I probably don't know. And I'm not going to learn them just because it's in there. And that's the same as the periodic table. That's the approach you need to take. It's there if you need it. And often you will refer to this atom a lot, this element, this element, this element, this element, this element, this element. You won't really talk about this one or any of these. Or really most of these. Maybe this, maybe that. You see how you can't really learn all these things because there's actually still 25 ones that you do talk about a lot, but there's probably about 85 that you don't. So it doesn't make sense for us to go ahead and learn everything here. But what we do need to know is how this thing works. So if I want to find out the name of the element, I look under the symbol. If I want to find out how many protons it has, I look at the atomic number. If I want to find out a total atomic mass, which is the number of protons added to the number of neutrons, I look at that number below it. So everything we have around us is just lots and lots of different ones of these in different combinations of molecules. So right now we're talking, I'm drinking its juice, but it's made of water. So I've got H2O. So I'm talking through this one and this one in my drink. I obviously talked about glucose, which is definitely in our bodies all the time, every day of our lives. So we've got C, we've got H, and we've got O. Now we're breathing in air, which is lots of nitrogen, some oxygen, some carbon, and actually a bit of argon as well. So everything around us is just lots of different combinations of molecules with these atoms in it. Now, we won't find all of these molecules, these atoms, these elements on Earth. Sometimes the elements have been discovered from exterior things coming to Earth, like space objects, so things like asteroids. And interestingly, very interestingly, Neil deGrasse Tyson, who is a physicist in America, who's famous for presenting TV shows about space, has said that the first trillionaire, so the person who not earns $1 billion, that's Jeff Bezos or all the other rich people, the person who will be a trillionaire is the person who can mine the materials of an asteroid, so take out those materials and use them on Earth. So we could find out new elements if new things arrive on Earth, but everything we've found so far is what we've been able to find. And actually, when we get to elements further down near where I say 118, that's when we really can't see these elements for longer than a millisecond before they change into a different element. So elements can kind of be a bit confusing. They can fall very quickly into reactions that mean we miss them and we can't really learn much about them. What elements can't do is just fully convert to another element. So I did say they change, but that's not because it just puts on a new jacket and becomes a new element. It's changing because it reacts away. So a lot of our elements we have are still an element, but they're involved in something else. But we can't really see them because now it's a molecule and it's not an element. So that's our periodic table. Again, you should never learn this. And I always see students like, should I learn the periodic table? No. Don't learn the periodic table, but do learn where the atomic number is and what it means in terms of how many protons. Learn the symbol if you want. You don't need to learn all the symbols, but I recommend knowing the symbol for carbon, knowing the symbol for nitrogen, for oxygen, for chlorine, because you get asked about that all the time in acids and bases. You could learn about this as a noble gas, this as a noble gas, sodium. Learn the symbol. It's a 2-second job. Learn potassium. You could learn maybe magnesium, but that one makes sense. And maybe one that just confused a lot of people is iron, wherever it is. I can't find it there. Fe. Now, Fe is the symbol for iron. It doesn't really make much logical sense because you might be thinking iridium is the symbol for iron. If you're thinking Ir is the symbol for iron, they probably discovered this one when English was talked more, and maybe they discovered this one when they were talking more in weird Latin kind of English. They called it ferrous, something like that, based on some other, I don't know, old chemists were weird and had their ways. But IR has already been taken, so think of it like that. IR, we can't call iron that because we've already got it reserved for something else. That's why we have all these weird symbols. And some symbols, like I said, are 2 letters and some symbols are 1. So it's worth having a good look at this and maybe learning the symbols of a few, meaning 10, not all of them. Okay, cool. So elements, big grid, like a dictionary, super useful. I don't know everything on there, and I have done chemistry for a very long time. So let's summarize everything we know. Now, I'm not going to spend too long on this because we do have other things to talk about, but I will say that, as we have said, this is an atom. Now, atoms could be represented as spheres, which I can't really draw with my tiny pen and my inability to draw, maybe like that. So these are 3-dimensional. I don't think these are kind of flat counters, 3-dimensional. So if you ever have something ordered on the internet and you get polystyrene beads, that's basically a huge version of an atom. They're way smaller than that though. So I could have an atom of oxygen. It would technically kind of be a sphere, but when we get lazy in chemistry, we can just write O instead of drawing a sphere with an O in it. Instead of writing a sphere with an H in it, we just might write H. And when we have water, we have H2O. So I'm going to draw the O connected to two H's. Now, if you're wondering why is it H2O like that and not maybe a hydrogen connected to a hydrogen and an oxygen over there, this is something that you would learn in a later topic, and generally it's something that you would just learn. You would start to learn how hydrogen can't bond to itself in the presence of another atom and other things like that. But for now, if you're wondering how to connect the atoms together, that's something you do need to learn. So obviously the only one we really need to know right now is water. So for water, we should know that oxygen is connected to two hydrogens because H2O. So we should only be seeing one oxygen, but interestingly, hydrogens do not connect to each other. They only connect through the oxygen. Again, you don't need to know why that is. It's to do with the fact that hydrogen cannot bond to two things at once, can only bond to itself or another thing and not two things at once. And you will learn these things as you learn more, but what you can really do is just, if you want to, research what the molecule is and see who's connected to what. Kind of rules like this person can't go with this person, but they want to go with this person. They don't want to sit next to this person, but they will sit with next person. That's how our elements kind of behave. So that's water. Now, again, we could have things that are classed as a molecule. Now, molecules are things like H2, H2O, N2, thinking of more HCl, NaOH, and my favorite, C6H12O6. These are all molecules. Now I'm going to talk about compounds. And I'm going to circle the molecules I've mentioned that are also compounds. And I want to see if you would pick the same ones as me. So have a think now which ones you would circle, which would be considered compounds. Have a think. Don't need to say anything. Don't need to do anything. Just think. Free. And what you can say is compounds should be things with different elements in them. This has hydrogen and oxygen, so this is a compound. H2O. HCl, is that a compound? Does it have two or more different elements? Yes, hydrogen and chlorine, HCl. Now, N2, is this an element? Does it have more than two, is this a compound? Does it have more than two elements in there? No, it's not a compound because there's only nitrogen. There's no other things in there. It's just nitrogen. So it must be a molecule, but not a compound. This is obviously a compound because there's three different elements, C6H12O6. Some of you might recognize that's glucose. Well done if you do. This is sodium hydroxide. Again, the names you definitely don't need to learn, but I would call it by its name. Sodium hydroxide, hydrogen oxide. Sodium, one element. Oxygen, another element. Hydrogen, another element. So I'm going to write NaOH over there. So now we know our elements. We know that there's three of them. That's definitely a compound. So that means these two are not compounds because they only contain themselves in the molecule. But can you see how everything is still a molecule, but only these ones are compounds? So that's our kind of relationship between the two. That is confusing for a lot of people, so don't worry if that kind of boggles you a bit. Okay, cool. Now, I think I've summarized what I wanted to say prior to getting into today's session. So now I open up the questions, not on Teams. So I'm going to go ahead and close those questions. And you can ask me questions on here. Now I'm going to see your question before I publish it to everyone else. But if I like your question, I will put it there for everyone to see and talk about it. So what you need to do now is you need to go onto Microsoft Teams. Sorry, not Microsoft Teams. You need to go to Slido and you can ask me a question. Try and keep it to today's topic. Try and actually ask me a question that you either want to know because it's definitely important to today's learning because you don't really understand something. Or if you're slightly interested in something, please don't ask me really advanced physics topics because I am a chemist, not a physicist. So, yeah. So again, the questions are going to come to me. Okay, I'm just going to read these ones out, but I'm not going to really share them because I don't know. So why is iron and Fe not IR? I don't know. I assume IR was discovered first. I don't know the first chemical element. I don't really know much history. That would be more history, I guess. Okay, I'm going to dismiss ones that I think are physics. So if I don't answer your question, it's either because someone's already asked it or it's considered physics, which wouldn't be appropriate for today. Okay, so I'm going to present these now. Hopefully this works. I don't know why it's not coming up. Okay. Why is it not doing it? Don't know why it's not presenting these questions, but let's try this one. Oh, sorry, I didn't mean to do that. Can atoms be created or destroyed? No, because that's a law of the universe that everything that's kind of been discovered on Earth is just kind of arrived here. We don't know why it's here. If I knew that, I would know some groundbreaking theory that would make me I don't know, the prophecy of the Earth. We don't know why we're here. Obviously, there's a lot of different theories. A lot of religions talk about those theories. So maybe you identify with one of those theories through religion, or maybe you have read some stuff in physics about why we might be here. A lot of them don't really talk about why, though. They just talk about how we got here. And the reason of why atoms exist is the same as how atoms exist. We don't know. But what we do know is we can't make more of them. If we could, we'd probably know why we could. And we can't destroy them. We can use them. We could try not to go near them if they're toxic, but we can't make them or destroy them. So I've answered that one. Still not being able to present my questions. It's really annoying. Let me try this one. I'm just going to try and get my questions up one more time on the screen. Okay. No, won't work. Why can hydrogen only bond to one other atom? So hydrogen's very small and it's not able to pull atoms towards itself. We can't really hold them towards itself without, we just have to let the atom do what it wants. The atom is not strong enough to pull atoms towards itself. That ability to pull atoms towards itself is called electronegativity. It's like a feature of the atom. Hydrogen doesn't have any. The other elements do, hydrogen does not. It's just a feature of hydrogen. Okay, cool. Are there less atoms in a molecule? Then it would be a smaller molecule. If there were less atoms in a molecule, then it would be a smaller molecule, and then some other ones would be, okay. Actually, I realized I was on the wrong section, so I'm going to try this. Are we technically made of stars because the elements in us come from stars? Yes, we technically are if we believe that the universe was created in this way where there was a big bang and there was lots of elements being sprayed out into space, and we came onto the Earth somehow through some living reason, which we don't know, through these elements coming together. Then we evolved and became humans. That theory does support the idea that we are made of stardust, but it is only a theory. So we have to think here that things are not defined. We do not know what's actually the correct idea. There's been lots of people thinking all these different things, but there's not been one way. It's like saying, think of a shape. Someone's going to think hexagon, someone's going to think square, someone's going to think circle. I didn't say which one, so no one's wrong. It's this idea that we all have different theories and we can't really prove them. So that's physics for you. Can atoms be created? We've done that. In a human body, there are 7 octillion atoms. How do people count that? There's no real reason to count that, but what someone would have done is said, okay, in a mass of flesh, there is this much of this element which weighs this much, therefore there must be this many atoms in the entire body by doing some multiplication. So it's a complete estimate. They would be doing some maths and it would be probably not true. Is a compound 2 or more different types of atoms that are chemically bonded together? Yes, well done. Nice. Why do some atoms bond more than once? Again, it's to do with this strength of how strong the atoms are at pulling other atoms towards themselves. Some atoms have got a little bit more strength left over, so not one bond, they can pull two. It's all to do with the atom's kind of identity, which is all to do with the number of protons, electrons, and neutrons you would see. And that is quite a hard topic, so we won't be talking about that in much detail, but it's because of those kind of identities of the atoms that dictate how it bonds. So it's great that you're thinking about that, because that shows that you're already thinking about the next step. Why do some atoms bond more than once? It would be for that reason. Can atoms die? No, because they're not living things. These are just things that exist. We don't know why they're here. We don't know how to get rid of them. We don't know how to make them. Are atoms just there in the world? Yes. How are atoms created? We don't know. Is there a way that an element can form into a compound in a chemical reaction? Yeah, it can rearrange itself when it sees another element that's reactive. So maybe if you're a cesium atom, as soon as you see water, you're like, oh, let me just rearrange myself and insert myself into the water molecule and kick another atom out. That's what some atoms do. They kick atoms out and they steal the huddle. So you can imagine them like groups of people. The minute you start thinking of chemistry as kind of learning about what little groups of people are doing, but instead of people, they're elements, the easier it might become. Cool. Yep. I'm not going to be able to answer them all, but this is a good start. So I'm going to pause there because actually we've got 3 minutes until our break. I think. Let me just check what time it is. We're not actually in the book topic of today. What I've been doing for the first hour is recapping. The reason why I'm recapping is the material that we're about to learn, organic chemistry, isn't typically discussed at year 7. It's normally discussed in maybe year 10. But because we're year 7, we might be a little bit around the age of year 7. We can't just go straight into this because I don't want it to get confused, and it is a confusing topic. You'll hear about year 10s complain about organic chemistry. Let's not complain about organic chemistry. Let's be clear on it. So to be clear on it, we kind of have to do a bit of a summarize. So I don't want to spend too long summarizing what I'm summarizing. How can glass be a liquid? I didn't see that question actually. I think it's just disappeared. Sorry if that was you. Can you separate compounds? Yes, you can separate compounds based on their boiling point and reactivity. In exams, we have to memorize all the symbols. No, but I've memorized a few, like carbon symbol, nitrogen symbol, chlorine symbol. I can write a few down for you to ones that we memorize, or moderator might be able to help you remember which ones are important. How many atoms are in animals? We can't really tell because they're so small. For clarity, there would be 10 times 10 to the 25 atoms of carbon in 12 grams of carbon. And we are obviously much bigger than 12 grams, but we are actually made predominantly of carbon. So if someone weighs, I don't know, 100 kilograms, then 100 kilograms times 12 times 10 to the 23, you can see what we're getting at, a very big number. How can glass be a liquid when it always looks solid? It is a solid, but you could maybe heat it to such a high temperature that the compounds that make up glass jiggle around a bit, and that makes it a liquid. How many protons, neutrons, electrons are there in the average atom? There is no average atom. There might be one atom that's more abundantly found in the earth, maybe like silicon, it's in rock, but there's no average atom. There's 118 different types of atom. Who knows which one we have? We've done that one. How many atoms are in animals? We can't do that one. Okay, I'm going to close these questions, but good questions. Thank you for your participation. The time is now 11:05. I'm just trying to see what time I said a break would happen. Oh, we've got 21 minutes. Amazing. Okay, cool. So we're going to end our Q&A. Thank you for your fun. Now let's talk about what I want to talk about today, carbon chemistry. So now we're in organic chemistry. This is still my slide, so you won't have this material. But now we are looking at the stuff that a year 10 would look at. So go us. What is it? This is a molecule. Now, this molecule is methane. If you have done a fart in the last hour, you would have done a bit of this yourself. Well done. You've made this in your body. Now, this is carbon, hydrogen, 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 hydrogen. So we should be thinking, what is the chemical formula for this? And if I count my hydrogens, I have 4. And if I count my carbons, I have 1. So I should be writing C. I don't want to write a 1 because I don't write 1s. But I do write H because that's the next element, and I do write 4. So this is CH4. Is it a compound? Yes. Why? Because the elements are different. Is it a molecule? Yes, because all compounds are molecules. See how I get that wrong, even though I'm talking it out loud? It's easy to mess up. This is a compound, and this is a molecule. Now, the reason why we're talking about this is very flammable. So technically, your farts are flammable. How fun! And it doesn't smell. So when you do a fart and it smells, what you're actually smelling is poop particles and this air, this gas, methane, rushing through that. So you're not smelling methane. Methane actually doesn't have a smell. When you're farting, you're producing methane, but you're not smelling the methane. Methane doesn't have a smell. Methane is flammable. Now, flammable means it burns well. So a flammable means it reacts and burns with oxygen. So I can write an equation here. I could say